Let me put back before you the frequency interpretation first, and then we will see how it is similar to the time interpretation that we had a few minutes ago. So, the frequency interpretation is like this. If you look at it, this is essentially a constant term, its magnitude is 1. This is again a constant 1 by 2 pi. So, one need not pay too much of attention to these two terms. Essentially, it is this integral which is important. In this integral, what are we doing? We are multiplying the Fourier transform of the function which is being analyzed, that is x, the Fourier transform is x cap of capital omega, by the Fourier transform of the window shifted to lie around capital omega naught. So, we are trying to analyze the content of the Fourier transform around omega equal to omega naught, and we are doing so at the point t equal to tau naught, if you please, because we are taking the inverse Fourier transform here. If you will just go back a few steps, we had the expression for the short time Fourier transform in time. Let me put back that expression for you. That expression is here. What did we do there? We did exactly a dual thing in time. So, we had this is, you see, if you before we calculated, we had this essentially as a time expression, and with this time expression what we did was the following. We multiplied x t by a translate. So, we extracted information of x t around the point t equal to tau naught, and then took a Fourier transform at the point omega equal to omega naught. This completes the beauty of duality in the interpretation. We are doing exactly the dual of what we have done in time in frequency. That is what we have said. The operation is very similar in time and frequency. It extracts a region of time, and it also simultaneously extracts a region of frequency. So, in a certain sense, the short time Fourier transform was a very good idea when it came, although when they used the rectangular window it was a bad idea, and the rectangular window was not sufficient for that reason. You had to taper off the window at both ends to make the function continuous. In fact, all this is also the basis of the idea of windowed FIR filter design in discrete time signal processing. People talk about designing finite impulse response filters using windows. Now, the ideas that we have talked about here are also replicated there in a slightly different context, but let me not go into that for the moment. Come back to this point. So, short time Fourier transform is one way of tiling the time frequency plane. What are the tiles doing in the short time Fourier transform? We must try and visualize them. So, in the STFT, we have fixed shape tiles, you may call them that, fixed shape tiles. Tau naught is a movement along time. And simultaneously, omega naught is a movement along frequency or angular frequency, if you please. So, in fact, I think it will be best to understand this graphically. What we are saying is, we have this time frequency plane as we constructed the last time. And in fact, the time frame is indexed by tau naught, and the frequency frame, the frequency region is indexed by capital omega naught, different values. So, at a particular tau naught and omega naught, what the short time Fourier transform does is to extract information in a region of the time frequency plane spread around tau naught and omega naught, where this is indicative of the time spread or twice the time spread of V, and this is indicative of twice the frequency spread of V. And what we are saying is, we can visualize this, think of this as a tile now, and visualize this tile as being moved along this two-dimensional plane, you know. So, forget about these axes for the moment, just visualize that tile, just visualize the plane underneath as the time frequency plane and this tile moving around. For different tau naught and omega naught, that is what we are doing. The shape is unchanged, that is important, we should mark it here, shape unchanged.